Okay, in this lesson, we are going to be looking at a bunch of different sequences, okay? If you recall, a sequence is a set of numbers that it has some sort of a pattern to it, okay? Sometimes it's a finite sequence, which means it has a fixed number of terms, which means basically it stops somewhere, okay? If it's an infinite sequence, it has an infinite number of terms and it goes on forever and ever and ever and ever and ever, okay? So here's some examples. Um, this top sequence is finite because it stops at the number 25. So this one would be finite. Okay. This one would be infinite. It goes on forever because of all the dot, 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 dots that you see. This one also goes on forever with all the dot, 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 dots. This is infinite. And then the last one would be infinite also. Okay. Um, we were going to look at specifically some kinds of sequences today called arithmetic and geometric, which I know you've studied before. Arithmetic means when you add really or subtract, because subtracting is adding a negative, to get to the next number every single time. So for instance, this one I add 5, add 5, add 5, add 5, that's arithmetic. Um, Geometric, you multiply by the same number. And by the way, dividing by 2 is the same as multiplying by 1/2. So even though it seems like you're dividing, you're really multiplying by a fraction. So when you multiply and divide, that's a geometric sequence. Here I would multiply by 2. 4 times 2 is 8. 8 times 2 is 16. I always multiply by 2 to get to the next number. That is a geometric sequence. And we will look a little bit more specifically at those in a minute. Okay, here you first of all just have to figure out how to read some notation that sequences have. So all this is saying is this is a little formula that's saying no matter this is your term number. Okay, that's your term number. All this formula is saying to do is take your term number in here, square it, and subtract 1. Okay, that's what this formula is telling us to do. So for instance, if I want you to find the first term, which I would denote as A1, I would want you to take 1, square it, and subtract 1. And obviously I get 0. To find A2, which is the second term on the list, I would want you to take 2, square it, subtract 1, and you get 3. Okay, I think you can kind of figure out how that goes. But the first term would be 0, the second term would be 3, the third term would be 8, the fourth term would be 15, and the fifth term would be 24. Okay, pretty easy to do. There's the first 5 terms. Now, if I want you to find the 100th term, which is A100, I would want you to take 100 and square it and subtract 1. And you can certainly do that. You can stick it into your calculator and you can get a big honking number. Your calculator will spit it out, I am sure, in scientific notation, but that's how you would do it. Okay? I'm not going to take the time to actually write the decimal down, but that's what you would do. Then, and those formulas, by the way, are called explicit. Explicit formulas mean I can find any term number. I can find the 100th term number right away by just simply plugging the term number into the formula. If you have recursive formulas, which these are, you can't find a term until you know the one before it, which is kind of a pain. Okay? So what this is saying, this formula right here is saying, to find the term you want, take 2 times this n minus 1 right here would be the term before it. So in other words, to find the fifth term, I have to take 2 times b5 minus 1, which is the fourth term. To find the fifth term, I have to take 2 times the fourth term. So I can't find the fifth term unless I know the fourth term, which is a major pain in the butt. Okay, but sometimes they write formulas like this. So on this sequence, I do know 3 is the first term. Okay, to find the second term, that's like saying b2 equals 2 times b to the 2 minus 1, which is 2 times b to the 1. Okay, well, I know b to the 1 is 3, so I go and I plug it in, and 2 times 3 is 6. Okay, to find the third term, I'm going to take 2 times the term before it. So I'm going to take 2 times the term before it, which is 6, to get 12. To find the fourth term, I take 2 times the term before it, which is 12, to get 24. To find the fifth term, I take 2 times the term before it, which is the fourth term, which happens to be 24, and I would get 48. And I think you can kind of see a pattern. The problem with recursive formulas is this. If I want to find the 100th term, I have to take 2 times the 99th term. I'm using B's, not A's, sorry. If I want to find the 100th term, I have to take 2 times the 99th term. Well, if I don't know the 99th term, then I have to find it. And I can't find the 99th until I know the 98th, and you can see the problem. Recursive formulas aren't useful that way. Okay? Here's another recursive formula that I just want you to get used to the notation on. Excuse me. Obviously, I'm giving you the first term, and I'm giving you the second term. Okay? This is saying wherever you're at to find 2 terms later, we're going to just call this Bn. And if 1 is n, then 2 is n plus 1. Okay? The third term then, do you see how it would be n plus 2? Okay, so what this is saying is, for instance, to find the third term, I can take the first term and the second term and add them together. Okay, so I'm taking the first term, which is 3 plus 5, add them together to get 8. To find the fourth term, I'm going to take B2 plus B3. So you're taking always the 2 terms before it, add it together. Okay, so that would be 5 plus 8, which is 13. To find B5, I would take B3 plus B4. Okay, which would be 8 plus 13, which would be 21. Okay, and you can keep that pattern. You're always taking the 2 terms before it, adding it together. That's what that notation is telling you. Again, to find B100, I couldn't find it unless I knew B98 and B99, which I don't in this case, so I'm not going to take the time to do it. I just want to show you the downfalls of recursive formulas. Okay. Then we're going to look at sequences that either converge or diverge, okay? And we'll kind of look at this in a minute, along with some rules that help you find limits, okay? So if basically it has a limit that is a finite number, that means it's not infinity, okay? That means it approaches 0 or 1 or 1/2 or whatever, then it converges. If the limit, and by the way, it's the limit as you approach infinity, so it's the limit as you're moving off the right side of the graph. If the limit as you're approaching infinity is either infinite or it doesn't exist, and I'll show you some examples, then it is said that the sequence diverges. Okay? There's some more rules here. These are in the corner of your notes, so I want you to pay attention to this because we'll pop back up on this in a minute. Okay? Here is a sequence. Okay, so I want you to think about it a couple of different ways. So first of all, this is like 2. And by the way, this is like 2 over 1. I can rate 1 as 2 over 2, and then I have 2 over 3. 1/2 right here could be 2 over 4. Then I have 2 over 5. I think the next one you can see would be 2 over 6, which is the same as 1/3. They might have it written as 1/3. Then 2 over 7, then 2 over 8, which is the same as 1/4. And I think you can see what's happening with your decimals. Your decimals are getting smaller and smaller and smaller and smaller and smaller. If this is the function, by the way, or the sequence that we're trying to decide if it converges or diverges, it might help for you to graph that. If you graph it, it looks like this. Okay, as I move off the right side of that graph, so as I move off here on the right side of that graph, my line is getting closer and closer and closer and closer and closer to the number 0. You can see I started with the number 2. I'm at the fraction 1/2, 1/3, 1/4. It's getting smaller and smaller and smaller and smaller and smaller. But it's never going to hit 0. It gets really, really close to 0 though. And so the limit is 0. And because the limit is 0, it has a limit and it converges to 0. Okay. And we'll talk more about that in a minute. If you look at the graph and it did something like this, then you can see that the limit reaches infinity up here. And if the limit reaches infinity, then it diverges. Okay? So here we go. We're going to practice this, and we're actually going to use those rules that are in the upper right-hand corner of your notes. Okay? So the first thing it says is well, if I'm looking at the first example is asking me to find the limit of 1 over x. So I'm following that rule, rule number 2, that says if the degree of the numerator is less than the degree of the denominator, the limit is 0. Okay, so this is like having x to the 0 up here because x to the 0 is 1. Okay, so in this particular example, the degree on my, and by the degree is you go by the exponents on your x. Okay, that tells you the degree, the highest exponent on your x that you see. Again, this is x to the 0. So the degree on the numerator is less than the degree of the denominator. So this limit is 0. Because 0 is a number, this is said to converge. It converges to 0. Okay? Here again, the exponent on my variable, this is like having x to the 0, less than having x to the 1. My numerator's degree is smaller than my denominator's degree. My limit is 0, and it converges. I would say it converges to 0. Same thing here. This is x to the 0. My limit is 0. It converges. Okay. One more. My degree up here, the highest exponent I see in my numerator is x to the 1. But in my denominator, I have x to the 2. So the biggest exponent I see on my x in my numerator is still smaller than my denominator. This is still 0, and it converges. So all those top rows converge. Okay? In the next row, every single one of them have a numerator whose degree is higher than what you see in the denominator. Okay? Here I have an x to the 3rd. Here I don't even have any x's, so I can think about it as x to the 0. When that happens, when the degree in the numerator is bigger than the degree in the denominator, and that's the same thing here, x to the 1, x to the 0. X squared, x to the 1. In every single one of those cases, same thing down here. This is x to the 3rd. Oh, not down there. Sorry. Okay. When you're, sorry, I'm trying to refocus here. Anyways, when the degree on your numerator is greater than the degree of the denominator, the limit is infinity. Okay, so this one would be infinite, this one would be infinite, this one would be infinite. When your limit is infinity, then it diverges. All of those diverge. Every single one of these diverges. Okay. All right, then when the degree in the numerator is less than the degree in the denominator, it is 0. So that's the same thing that's happening here. Okay, the degree in the numerator is less than the degree in the denominator, it's 0. Numerator degree of 3, denominator degree of 5, 0. Ooh, this one. Numerator, the highest exponent I see is 7. The lowest exponent I see is 4. Okay, these two right here, because they go to 0, converges. This one, when the degree in the numerator is bigger than the degree in the denominator, it goes to infinity and it diverges. I hope you can see the pattern now. Okay, hopefully you can. I'm going to skip those last couple. No, I'm not. Okay. The next rule, which is rule number 2 on your rules sheet that says up there, it says if the degree of the numerator is the same, sorry, degree, rule number 1. If the degree of the numerator is the same as the degree of the denominator, the limit is the ratio of the leading coefficients, and that probably is Greek to you. Here's what I want you to notice. X to the fourth, x to the fourth. They have the same degree. Your limit will be this ratio right here, which is 2/9. Okay, because that's a number and not infinity, it converges. So this one would converge to 2/9. Here, highest degree is x to the third, highest degree is x to the third. It's the same. Your ratio will be 11/2. Okay, this also converges. And then the last one, you probably don't remember, but I just want to show you this weird case because sometimes this happens. The graph of sine goes something like this, okay? And it doesn't have a limit because it just simply oscillates. So the limit itself doesn't exist. And when it doesn't exist, it also diverges. Okay? So there's that. Now, moving on to these. Okay, so hopefully you can kind of see what happens here and decide if your numbers are going to approach infinity or approach a number or approach whatever. Okay, here you've got a pattern. I'm giving you a formula there. My numerator is small. My degree on my numerator, because this is n to the 0, is smaller than the degree of my denominator. So the limit is infinity, which means it diverges. Okay. Here, I hope you can see, this is 2/1, 3/2, 4/3. The next one would be 5/4, 6/5, 7/8, 8/7, 9/8, 10/9. So I hope you're seeing this is 2, 1.5, 1 1/3, 1 1/4, 1 1/5, 1 1/6. That should be 1 1/7, 1 1/8, 1 1/9. The next one will be 1 1/10, 1 1/11, 1 1/12, 1 1. They're all getting really, really close to the number 1. Okay. In fact, what I would say is that this converges to 1. Okay. Then the next one, 2, 4, 6, 8, 10. I think you can see it's going to go 12, 14, 16. It's going to keep getting bigger, 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 bigger. This one has a limit of infinity, so it diverges. Okay, and then the next one just keeps oscillating back and forth between -1 and 1, -1 and 1, -1 and 1, -1 and 1. The limit on this one doesn't exist because it doesn't go to anything or approach anything. So the limit doesn't exist, and it diverges also. All right, I think I'm going to stop that video right here because as I'm teaching this, I'm realizing I probably need to split this lesson. So I'm going to stop right here.